Hello everyone, my name is Amir Hussein Abbasqui. Welcome back to the second session of Transformer Architecture series. Um, First of all, I want to talk about something that one of my friends asked me um, some days ago. Um, he asked me that, okay, we know that in the simple architecture of transformer, which we have one encoder and one with decoder, how these parts are connected together. But when we are saying that we have 6 encoders and 6 decoders, basically how we are connecting these things. Uh, the image that is shown to you is how decoders and encoders are connected to each other. Basically, each encoder encodes the result of the previous encoder uh, until the latest bit that we wanted to have. For example, when we want to have 6 encoders, as a result, we encode the input, which is a sentence in, I think it is in French, into up to 6 layers, and then the decoders, all of them, gets the last encoder result and uses the output of the previous decoder by itself to decode the sentence, and this is how 6 encoders and 6 decoders are connected to each other. But let me explain multi-head attention to you. In the previous session we talked about scaled out product attention and how single attention is working, but now we are going to talk about multi-head attention. The main thing that we were talking about, why we should use transformer architecture and we use attention and feed-forward neural networks, was that in comparison with recurrent neural networks, we want to have more speed, and in addition to that, this speed can help us to converge not only faster but better. So we know that a scaled product and feed-forward network can help us, but the problem here is that we have two large matrices when we have a big layer in our neural network. So what we have to do in this scenario, we use multi-head attention. Instead of performing a single attention function, they use something else. Let me turn on my comments. Yes, okay. This is better. Instead of performing a single attention function with d dimensions, values, and queries, we found it's beneficial to linearly project the queries. What are they saying is basically, instead of using a single attention, they are going to uh, divide it into different sections and find the results and then concat them somehow to find uh, the main result of the attention. So they do it each times with different learned linear projections to dk, dk, and dv dimensions. Respectively, on each of these projected versions of queries, keys and values were we then perform the attention function in parallel, yielding dv dimensional output values. These are concatenated and once again projected, resulting in the final values as depicted in figure 2. Let me explain it based on this image in here. As we can see, again we have 3 matrices, queries, keys, and values in here. Then we have a linear projection. This is where we do the projection. So if I'm going to say here is projection, then in here we have h time scaled dot product for each projected matrices, and then in here we are concatenating the result of attention heads. Each time that we are calculating this is called attention head. Let me make this better for you. And finally, we are going to do the projection again. Why we do projection again? Because finding the attention is not just simply making divided parts and then concatenating them. We know that the attention is real attention of each part is related to another, so we need to do another projection here. So the linear layer in this section is doing that thing. So this is how it works. Now let's look at this formula here, which introduces the multi-head attention. As we can see, for each head we find this attention. As we can see, why we are using wi. Wi is basically representing that projection, and instead of passing the all keys and queries and values, we are passing the projection, the divided part of the sum part of our queries, keys, and values. Then we are concatenating them, and then use this projection matrix to produce the final result. It says that WO is exactly how we are getting the final result. We know that our final result should be wanted dimension, so this is how it's exactly work. In their paper they are using 8 heads, but this can be different for other models that are based on transformer architecture. I cannot remember exactly how many heads, for example, BERT has, but I think it's not equal to 8. So this is how exactly multi-head attention works. Now let's implement it in our model. So for Pytorch, I'm going to create a new file, multi-head attention, and not only we need torch neural network, we also need to use data scale that product we implemented in the last session. Some models, it's better to say, from .scale.product import. What was the name of that thing that I was implementing? Scale.product, okay, so now we are going to create a new class called multi-head attention, which inherits from the module of neural network of Pytorch. Then we have its constructor. As we know, we need the number of heads and the dimension of model, so we're passing them, and then we are going to say, first of all, call the constructor of NN module, which is multi-head attention. So now that we have all of these things, we need to save these parameters. So number of heads is saved. Attention is scale.product. thing. We have matrices of queries. This linear demodeled, and we have this thing for keys and values as well. And then we have the weight of concat, which is WO in the paper. So concat is another linear layer which needs the model and the model. So this is exactly what is happening in the paper. If you look at this image, we have three linears, although it's based on the heads, but we have one linear per each of these values and queries and keys, and then we have a linear for the output. So this is what's happening here. This is for the queries, keys, and values, and this is for concatenation result. Next, we're going to implement forward function, which needs absolutely Q, K, and V. And as we know, we may need to mask something, but the default parameter for it is none. But we're going to talk about masking as well. Query key and value is equal to self dot this thing, self dot this linear layer, and this linear layer. In addition, K and V for the next one. The first time that you're doing this is you're using that product with weight matrices to do the projection, and then you need to split things. So you're going to say self dot split. Split is defined in an end module, so self dot split q self dot split k is it's not b, it's v, and self dot. We talk about the split a little further, but for now, just consider this as a splitting tensor by number of heads, as we need to pass them to the different heads of the attention. And now we say that the output and attention is the self dot attention q k v and mask equal to mask. Now we are saying that the output is self dot concat of out, and out then is equal to self dot w concat of out. So it's not that much hard, huh? Okay, so then we can return the output. Now we need to write a function for concat and split. So first let's talk about split, which have a tensor and it splits it based on the number of heads. Okay, it's not something hard, it's just batch size, length, and the model is tensor.size. Then we say that the dimension of tensor is the model divided by self, that's number of head. And now we can say that tensor, or better to say, we can return tensor that view, which is changing the creating different tensors in here. Tensor that view batch size is still the same. It's not different. The length is the same, but we are saying that we want, instead of having just D model, we are going to say we want to have n heads of the tensor. So this is how it's happening, and then we are going to make a transpose of that. And this is how a split works. And then we have concat function, which gets tensor, and now it's going to concat tensor to each other. So again, we need to do something like this: batch size, lengths, and all these things. And here, as we're going to concat these to each other, so we are just going to say D model is number of head, because as you know, here instead we have head, the tensor is the opposite of the last function, number of heads and the tensor. So then we can return tensor that transpose by this, and contiguous, and then we're going to view in number of batch size, length, and the model. Okay, we do not have any problem with here, I think, but about the contiguous, actually I found it on the internet. Let me see what is contiguous. Contiguous is continuous. I think I made a mistake in typo as well, but contiguous in Pytorch, what does it actually do? A contiguous tensor is a tensor whose elements are stored in a contiguous order without leaving any empty space between them. So it's not doing actually something very special here. It's just to make sure that all the values are one after another. It's just to making sure of that. So this is multi-head attention. It was not something hard at all. Now let's get back to TensorFlow. Now we're going to implement this thing in TensorFlow as well. Multi-head attention. Okay. Multi-head attention in TensorFlow isn't exactly the same. So multi-head attention, we have queries, keys, values, key masks, number of heads, and heads, better to say, which here as default is 8. We can say we could pass it in there, but I'm not going to talk about it in here. And we have drop out rate, which is by default equal. So let me do not talk about drop out, huh? Just implement the thing that was going to happen again there. And training is true, causality is false, and the scope is multi-head attention, multi-head attention. I'm not sure how should I pronounce that, but something like this. The model queries that get shape dot as list with creating a scope, variable scope, based on the scope given, and reuse is tf.auto reuse. We're going to have q, which is tf.layers.dense, which is the linear layer we had in Pytorch. Then we need to pass q the model and use bias, which is passed through. We have this thing for two other things as well, q, k, and v. So those things you're going to pass k and v. This was just the linear projection. Now we need to do that splitting. So we're going to set that q. Let me copy these lines, paste them in here. It's exactly like the same, but instead of these things, we need to say, we use to split function of TensorFlow. So tf.split q, number of heads, and axis, which is equal to 2, and axis here is equal to 0, because we are going to split in the axis number 2, and yeah, that's exactly happening. Then as we are going to concat them, we are doing it on axis 0. So instead of dense, we have tf.concat, and we need to copy this for these two things as well. Instead, we just need to change this as k and this as v. So that is easy. Please do not think that this concat is something happening in here. No, it's not this concat. It's just how the split function for splitting the main queries, keys, and values is happening in here. So this is how we should do it in TensorFlow. It's just splitting. This is the linear projection. This is the splitting, and then we need to find the attention of each one. So we say outputs is scale.product attention, which needs these things. So passing qkv, and then we have key image. So we need to pass causality. As I use dropouts, I can leave dropouts out of here because I think it's just make it hard. But I pass causality, yes, and training. But the scope is not changed, as I think. Yes, it's not changed. Now that we find the attention of each one, now we need to concat outputs. Okay, so we just say outputs is tf.concat of those results. So we say tf.split outputs, number of heads and heads, an axis 0, and this is an axis 2, is vice versa of what we have done in this section. Now that we have the output, we can add the queries or not. It's not that much important, but as we are not going to use a residual connection in here, we're just going to return the outputs. So this is how multi-head attention works in here. Although I'm going to mention that after this you can do normalization, you can do the residual collection based on the queries that you had, but we're not going to do that in here. So it's a simple implementation of multi-head attention, and I think that was so easy. Okay, yeah, that was it for this session. In the next session we are going to continue our progress. Our plan is to talk about the positional encoding, and then creating the blocks of encoder and decoder, and then concat them and finish this project and this series of videos. So to the next video, please stay safe. Goodbye.